最悪だ。これでないや。Okay, so okay, so let's sorry. So let's start lecture. 声が出ない。あ、なんだ。うん。Okay, so first, so this is, yeah, this is n equal to Suji algebra. N equal to algebra means, okay, there is two copies of the n equal 1 algebra. Okay, so this A, capital B, label the two Suji algebra. Okay, n equal 1 Suji algebra. So these are separated because this is the delta function here. So this is just two copies. Okay. But for this QQ commutator, for the n equal 1 algebra, there is no possibility to have a non-zero something here. But here, there is a two supersymmetry generator. So there's a possibility that there's another one because there is a epsilon tensor here. Okay, so these two epsilon tensor gives this is symmetric. Okay, and this is called central charge of the n equal 2 algebras. Okay, oh, another one is sorry, Q alpha double Q. This is called central charge. This is complex because this G should commute with any generator in here. I mean, it's commuted with a Suji generator, commuted with energy momentum here. Okay, so it's called central charge. Okay, this is a general. I mean, there's a theorem by Coleman-Mandula, and there's extension. And then this is possible. There's only the possible supersymmetric algebra for n equal 2 case. Okay. And here we consider the spectrum for the massive case, and we rotate this P by the Lorentz transformation to Pi equals 0. Pi is a space direction, P0 equals of course time. So it's this is energy, and this is there's no moment. Then we define these two types of the operator. This satisfies the canonical anti-commutation relation. Okay, from this algebra with this choice, this A and B satisfy this one. Okay. Others means other combinations like A, B, B, or A, B, daga, or something like that. A, B. It's all 0. So this is only a non-trivial one. So this means that there is a two decoupled fermions. Okay. Or there is alpha, so there's a four decoupled fermi. And then then this means M should be greater than the absolute value of Z. This is because if this is something, if I have alpha equal beta, then this is a BB daga or something like that. That it should be positive. I mean, actually, in the last lecture, we showed this is there we call R and R daga, it's C, so then C should be positive. That means M should be greater than 1. Sorry. Okay, so this, yeah. Sorry, again, this one? This is just a rewriting of this algebra. Sorry, either bracket has a. This this doesn't satisfy. This becomes a negative. Okay, and if we said as we R dagger, if this is C, then C should be 0. We showed it because of this is something like some absolute value of R, so C should be greater than 1. Greater than, I mean, C should be non-negative. So then. Yes. Actually, if we take some other combination or something like here we parameterize this and z bar or something like that to have this one. Okay. So they are not this is not symmetric combination, but. Okay, sorry. This is yes, here, sorry. M can be here M can be yes, sorry. Maybe this should be M. Yeah. Sorry. This is probably okay. Actually, there is some ambiguity for to square root or something like that. Then, actually, there is a choice here. But so forget about it, and then we have this one. Then, if M equal z, then b alpha equals 0. Okay, and SUSY of b alpha is not broken. Is not broken. Okay, and this b equals 0 means this b is represented by actually 0. Okay, so as we saw yesterday, this representation is half number of the states. Number of states is a half compared with generic state. I mean not saturating this bound. Okay, and this is called the BPS state. And this is called the BPS bound. Okay. Alpha. If m is this one, if for example v1 daga equal, if this is then something consider these VB types argument for any a. Then this becomes a b double squared plus b squared equal 0. That means this state itself should be 0. I mean, this BA equals 0 for any state. So that means B should be represented by 0 itself. Okay. Is a half compared with compared with MZ case. Okay, this is an analog of the actually this case is analog of the vacuum state or massless state. Okay. So that is usually represented by some charges, U1 charge, electric charge, magnetic charge, etc. So this is this state is it's like a vacuum state with some fixed charge. So this is the meaning of the BPS state. So as you saw before, for example, massless state becomes a half the number of the state. So this is like that. More precisely, this is called half BPS state because this is a half. For example, in equal 4 case, there can be a fourth BPS state or something like that. But here only half BPS state appear as a state. And okay, let us consider this n equal to supersymmetric n super YAMLs. This is a prototype of cyber-Witten theory or class C theories or M-theory component or everything. So, and these types of theory have same structure like Coulomb branch or something like that. But actually, later we will use n equal to superfield a bit, but yeah, it's a very complicated one. So we will use n equal 1 superfield notation to describe n equal 2 super YAMLs. This is also usable. So then, so in n equal 1 superfield, this theory, super YAMLs means there is no matter multiplet. Matter multiplet is called for n equal 2 case the hyper multiplet. So this means that there is only the vector multiplet in n equal 2. Okay. So this is okay. This n vector multiplet in n equal 1. Notation is W described by W alpha. This is the adjoint of the SUN. And this contains lambda x, lambda bar, and sorry, Vmx with a gauge field, and lambda is a wire Fermi. And of course, these are also the adjoint representation of the gauge group. And plus chiral multiplet. So this, yeah, n equal 1 vector multiplet cannot be n equal 2 because there is some copies. So we need to double these state. Actually, we add one chiral multiplet, phi. This, of course, contains psi x, phi x. And take this also as the adjoint representation of the gauge group. Okay, this is very special. Okay, these two, both of these two are adjoint representation. So there is a NC squared minus 1 component. Okay, and we take W equals 0, no superpotential here. So this also means this is massless and no Yukawa interaction or something like that. 5-4 interaction, no 5-4 interaction. So the only interaction in the theory is a gauge interaction, represented by the covariant derivative in a kinetic term. And then, so there's only gauge interaction. Then this, lambda and psi have same action. Okay. Okay, these two. So there's only the gauge interaction. So this, I mean, in the action, there is only the kinetic term for these fermions. Of course, kinetic term include the gauge interaction, but there's only the kinetic term. So these two kinetic terms, of course, is same. It's just use a kinetic term for the wire string. Okay, this means there is some symmetry. Exchange lambda psi. This is a symmetry. Okay, so this action has n equal 1 supersymmetry plus this Z2 symmetry. That means supersymmetry rate Vm and lambda, and supersymmetry rate psi and phi. But here there is some Z2 symmetry exchanging this lambda and psi. Okay. Okay. Then after this Z2 symmetry, this supersymmetry relate Vm and psi, and lambda and phi. Okay. So this supercharges are completely different from this original one. So there is a double. I mean, there's two copies of the supersymmetry. That means this theory is n equal 2. Okay. Okay. Okay, so this just consider the n equal 1 vector multiplet plus chiral multiplet without any interaction, with except gauge interaction. Then theory have n equal 2. Okay. So this theory has n equal. This is n equal 2 supersymmetric SN super Yamis. This is the definition. So this multiplet is called n equal 2 vector multiplet. Okay. So then what is the classical modular space? So this theory has some special property. This scalar is adjoint. Okay, so this is n equal vector multiplet always contains a scalar in adjoint representation. Then there's no F term, I mean, there's no superpotential. So classical modular space is given by this one, dA equals 0, D term condition. But here, this T is okay. Here, this notation for the general chiral multiplet, then this TA is NC squared minus 1 times NC squared minus 1 matrix. And this phi is NC minus 1 vector because adjoint representation contains dimension of the adjoint representation is the NC squared minus 1. Okay, so the number of the generator. And then, usually, in a usual notation of the adjoint field, is like this one. Okay. This Tn is a representation matrix for the fundamental field. So n means the fundamental. Okay. Okay. Usually we will denote adjoint fields are not like a vector but a matrix like this one. Okay. So A runs from NC 1 to NC minus. This is the usual notation of the adjoint field. Then this condition is written like this. So this is a vacuum condition, at least for the classical field. Yes. Size of what? Size of phi. This one. Yes, yes. Yeah. Here in this notation. Sorry. This one is different. This is phi equal. There is a NC minus 1 component. This one. Okay. This is a n by n matrix. No, sorry, this phi A is this one. This one, phi 1, phi 2, phi NC minus 1. A round, so, okay. So this is the user notation. But here, it's, yeah, for the general, this This is given by this is for the general representation. So it's not like a user notation of the agent representation. So just yeah, rewriting. Okay. Okay. This one? Sorry. A, sorry. Okay. Okay, repeated index is always summed. If all summed, okay, except I stress there's no sum. So yeah. Sorry. Okay. So then, to solve this equation, I introduce a Hermitian combination, phi plus phi dagger, and also phi minus phi dagger. This is anti-Hermitian, but anyway, if I introduce I here, then it becomes Hermitian. So we introduce this combination. Maybe I introduce I phi. So these two are Hermitian. And let us consider these types. And here D is diagonal. And U is unitary. Okay. Because this is a Hermitian, so you can always diagonalize this Hermitian matrix by the unitary matrix. Okay, and this D is a diagonal matrix representing the eigenvalue of the matrix. Okay, but here this U and U dagger is the same one. Then for the user, I mean, not if phi doesn't satisfy anything, then this E is something complicated. But here, because of the phi dagger, this is equivalent to D and E equals 0. And then E is also diagonal. But here for generic eigenvalue, generic D. Okay, because this is diagonal matrix, and if the eigenvalues are all different, then this E should be also diagonal. Okay. Then phi can be represented by phi is sum of these two. Sorry, so U is unitary. Sorry, this U. Sorry. U. This U. E. Here E is diagonal because of this this condition. For this class, if the phi satisfies this classical bucket condition, then it should be also diagonal. For generic D, generic D means eigenvalue of the D are all different. If it's same, like for example, it's D equals 0, then of course this doesn't say anything. So it's a singularity in a classical modular space. Okay, it's there is some non-abelian gauge groups remains. Okay. Anyway, this condition is classically for generic D means gauge group is completely. Sorry, I will explain. Sorry. So then phi equal a1 dot a1 a2 dot an 0 U dagger. Of course, this A is a summation of the eigenvalue of D and D plus E. So this A is complex. So this condition means this diagonal, this phi, this is a complex matrix, but we can diagonalize it by the unitary matrix. Okay, for this condition. Okay, so then the classical modular space is described by this A. Of course, there's identification by the while reflection. So we can, we can exchange these eigenvalues, but okay. And then, actually, we know this result. Actually, in a gauge invariant operator, this means okay. As we have shown for the n equal 1 case. Of course, n equal 2 is a special case of n equal 1. So the modular space is given, moduli of the modular space of the vacuum is by the chiral, gauge invariant operator constructed by the chiral superfield. In this case, there is only this adjoint. From the adjoint, only the gauge invariant or SUN invariant is these NC minus 1 things. Okay. Okay, this is same as in this component. It's same. Of course, you daga is cancelled in this expression. Okay, and there is no. Okay, so there is a NC minus 1 component, complex component. This also has a NC minus 1 component because trace phi equals 0 is sigma A equals 0. So there's one condition for this one. So then these two describe the same space. Then from this one, in almost all vacuum means these A's are all different cases. This case, this SUN is broken to U1 NC minus 1. Okay, U1 NC minus 1 is the diagonal part of the SUN. Okay. Okay, so in a SUN generator have something B1, B2, B. NC0. These phase represent U1, and there is some trace condition, so there is a U1 to NC minus 1. Okay, diagonal part is broken by this VV. Okay, and this is called Coulomb phase. Because this is abelian. Okay, so n equal to vector multiplicator with n equal to vector multiplicator, the theory tend to go to Coulomb branch or Coulomb phase like this. Okay, if there is a matter, hypermultiplicator, there is a called Higgs phase. It's have a hyperkähler structure or something like that. But at least at the origin of the hyperkähler, hypermultiplicator, there is some Coulomb phase like this in a vector multiplicator scalar. And below we will consider the only n equal 2 case because for the simplicity. Then phi equal just A minus AU. Okay, I inserted this 1 over 2 for convenience. I mean, and A and this is traceless. A plus minus A equals 0, so it's okay. And then you define U is a gauge invariant operator. It's defined by trace phi squared. In this case, this is only the modular in the theory. And in a classical theory, this is given by 1/2 times A squared. And then, semi-classically, we can compute Q and Q bar in this vacuum. And then we can compute also Z, what Z is because Z is anti-commutative of QQ. So if we can compute the QQ bar as a net charge, we can compute the Z as well. And the Z is then, after the computation, Z is represented by, in a semi-classically, by this without the theta function, but anyway. Is like this one. This is a gauge coupling. Phi is, of course, this phi. This En is Fn0, and this is epsilon 0. Sorry, epsilon up. Sorry, epsilon upper K L N F K L. Okay, so this is the electric field, and this is the magnetic field in a U1 case. Okay. Actually, this theory is broken to U1. This n equal to, sorry, n equal to, so this is U1 theory in low energy. So this part, this phi E, trace phi E means projection to the U1 part for this SU2 gauge field. Okay, and the point is this is given by this boundary. I mean, total divergence. Okay. Then, of course, total divergence, this is divergence of the E and divergence B represents electric charge and magnetic charge. And then, okay. Then this is given by the NEA plus NM tau A. So this is electric charge. This is a magnetic charge. It's quantized. Okay. So this is this is a Gauss law. I mean, yeah, divergence over divergence gives charge, and divergence gives charge. And here, it's this computation is theta equals 0, but we include theta, then it's become tau. Tau include I times 1 over G squared, something like that. So this is correct. So Z is like this one. And sorry, quantum mechanically, we define A such that Z equal ANE plus NM sum AD. So okay, This A semi-classically something square root of U or something like that, this A. But in quantum mechanically, we cannot trust anything for the semi-classical computation, but still we defined A as this formula is satisfied, okay? I mean, Z is a physical quantities, okay? So of course, NE is physical quantity, it's a charge. So then we define A as a proportionality of Z and NE. So it's this is the definition of A. And this means actually A is as we have seen. Actually, mass of the BPS state, we charge one case and the NM equals 0 case. So it's like an electric, like electron case. This is I mean, precise formula. It's exact formula. And here we define A as this one. So this should be A. So A is a mass of the BPS state. This is a definition of A. For the absolute value of the A, for the absolute value of the A. But there are some phases, but including it by this C. And the AD is some function of A. So now, are you okay? In n equal 2 superspace, n equal 2 superspace means just double the Fermi coordinate, 1, 2, and 1, 2. Okay. But this is a bit complicated, so I here just write down the what is the consequence in using this n equal 2 superspace. For the n equal 2 vector multiplet, it's described. Okay. For n equal 1 case, there is a scalar potential and super potential. That is kind of theory. But in n equal 2, these are somewhere combined into the one holomorphic function. So super potential is something lifted to n equal 2, a holomorphic function. It's called prepotential. And in n equal 1 language, action is written using this prepotential like okay, so that means Okay. So in an n equal 1 language, there is a vector multiplicator and a color multiplicator. And this A have some color multiplicator component. This A, small a, is like this A or this A here. And this capital A is some lift of the A into the n equal super multiplicator, vector multiplicator. Okay. So this is just a result, but yeah, important thing is scalar potential is given by this holomorphic function. And gauge coupling constant is also given by this prepotential. Okay, so if we know the prepotential, this holomorphic function, then we can decide the theory completely. Okay, except of course there is some derivative correction, higher order derivative correction. But so in low energy, the theory should be described by these things. Okay. So if we can fix the what is the f for this quantum n equal to field theory, then we solve the low energy theory completely. Okay, this is called Seiberg-Witten theory. So could you speak again? Fi terms. For this case, there's no, because this theory comes from the SU2 to broken to U1. So it's maybe it's from the U2 to U1 case we can add the Fi term. But here, if we include U1 into the 4-dimensional theory, then the theory is not asymptotically free. So it's not very defined. There's ambiguity. So here, so for the SU2 case, it's asymptotic free. So there's no ambiguity. So the theory should be determined by the matter content only. Okay, so we can fix this F completely without any other information around the UV cutoff or something like that. Okay. Okay, and of course this is holomorphic, so there's a chance to determine this using the way we saw yesterday or yes. Sorry, this one is called A, and it contains A as a lowest component. It's a scalar and describes U or something like that. Actually here. Okay. Okay. In if A is greater than lambda very much, this case that means a coupling constant around energy scale A is very weak. A is a vacuum excitation value of the theory. So this means theory is in a weak coupling. So we can do the instant expansion or weak coupling expansion. It includes also, of course, there is some loop terms and also instant effect. And as we have seen, this represents only the one loop terms, and this represents instant part. Because tau is related by this F. Okay, So tau is given by the one loop plus instanton. So this is lifting tau to this EF. And we will see later. This AD is this one. This is function A. This is given by derivative of this prepotential. And this is plus okay. Yeah, just I inserted here this expression, and then tau is derivative that one, and k equal imaginary part of AD. A. Actually, AD is mass of the represent the mass of the monopole. Okay. Yes. Sorry. Holomorphic means sorry. It's yeah. With if we allow singularity, so it's not a holomorphic, meromorphic or some. Yeah. It's yeah. It's yeah. Holomorphic means just there's no a bar a dagger here. Yes. It's okay. Yeah. We have some singular point. There, the holomorphy can be broken or something like that with this expression. Something like sorry. So yeah, people use holomorphic, but sometimes it means a meromorphic or more singular or something like that. And as you know, U1 gauge theory, Lorentz theory of this SQ2 theory is Coulomb field, so it's a U1 gauge theory, so it's abelian. So for the abelian case, we know there is the exact duality between the electric and magnetic field. I mean, if we exchange E and B, then Maxwell field, of course, invariant and that is represents the duality. Okay, so we know this one, and we can express this using path integral formalism. But here, I did not do that. But some consequence of this one is coupling constant is reversed or something like that. Okay, if the original theory is weak coupling, then the other one is strong. So electric magnetic duality is a strong weak duality. Okay, and because this is a free theory, so we can show it precisely. Okay. Actually, this is the only known exact. Only the duality we can trust truly. Okay. For n equal 4 superimage case, it's also believed S dual, but there's no of course proof. But here, this is just U1, so we have a proof for this duality. Okay, and then there's we can introduce a theta term. Then this means there is some. We use a different normalization, but we can think this tau goes to -1 over tau. If theta equals 0, this means gauge coupling constant is inversed. Okay, we can show that this one, and also there is a shift of the theta term. Okay, so then the low energy theory have these two symmetry or duality. Okay, and okay. If we associate these to the S and T, and of course, as you know, this is same as Riemann surface, I mean torus, but okay. So there is a duality of this SL to Z for this U1 gauge theory, as you know. Okay, this one. This SL to Z is generated by this generator S and T, ST something or ST inverse S something, and then we can have a sorry, this ABCD is take a integer. And of course, this is a special. I mean, determinant is 1. Okay. But this is SF2Z, not SF2R, because these are dependent by this 2, because of the charge conservation. Okay. So this is, in some sense, trivial result for the U1 case series. But yeah, of course, it's not trivial. But anyway. And we also see, this means, okay, if tau is represented by tau AD del A, then you can see this AD and A transforms by this SL to Z, like this one, as a vector, because of this one. Acting D here and acting D here, and then we can see this relation. And this one? No, yeah, actually, duality is given by these two generators. Okay, so this is an integer. So, yeah, if this theta is theta plus real or something, and then it becomes SL2R or something about that. It's related to the quantization of the charge or something like that. And we can also see this electric magnetic duality transforms, of course, electric charge and magnetic charge, like this combination. This you can check that because this exchange are E and B, so it's like exchange NM and NE for the S duality case. And T duality case, T transformation case, it's a bit difficult, but it's called Witten effect. If we change the theta, then some shift of the magnetic charge proportional to NE is occurs. So then we can see this relation. But it's a detail, so I will not explain the detail, but we can see this relation. And then actually, Z is a physical quantity, and this SL2Z is a duality. Duality means just a coordinate change, like a coordinate change. That is a change of the description. So Z should be invariant under this SL2Z. Okay, Z is like observable. We can find this is related to the mass of the theory, so it should be SL2Z invariant. Okay, then as you see, from this relation, tau is given by this, so this, and finally, this is gauge invariant. So our choice, this one, AD is given by, AD is given by this, is justified because this combination is indeed invariant. Okay. Okay, so AD is given by this one. And everything is driven by such a combination. And then, to constrain the prepotential, we consider some monodromy problem. I mean, moving in modular space. It means there's a U plane. U is a gauge multiple, so this is a nice one. And then we consider there's a infinity. Infinity is something infinity. And we consider some path in a modular space of the vacuum. And and see what happens. Means U equal R exponential I phi, and R is very large. This means that this outer region is like a weak coupling region, because U is very large. That means A is very large. A is very large means at the scale of A, gauge coupling U1 gauge coupling constant is very weak. So this infinity region is a semi-classical region. Then we can compute everything using use one loop effect plus instanton if we need it. And consider phi equal 0 to phi equal minus 2 pi. Actually, we want to go around this infinity, this direction. So that means this direction. Then, because U is A squared, that means after this rotation, A becomes minus A, because this is A squared. Okay? Here U go around, so this A to minus A. Of course, this is exponential phi, so A is like exponential to I phi something, and phi equals 0 to 2 pi, so this becomes exponential I pi, which one? Okay, and then it becomes minus 1. Okay, so U is of course a good coordinate in a modular space, but this A, should be, actually A, yes, and for the AD, AD is given by this one in a weak coupling limit plus ... Then this means AD is like minus AD plus 2A. Okay. Maybe you think this is not consistent because A should be invariant. I mean, around that we are moving back to the original point, but A changes. But this means this is okay because this means AD A is like a okay, so this This is represented by this infinity here. And this infinity is, of course, an element of SL to Z. Okay, so this is just a SL to Z transformation. Actually, there is some ambiguity in the description in A and AD. So this is okay. Okay. So this is called monodromy. And and this is not one. So if there's nothing inside here, then yeah, we can shrink this one, and then it's contradict. So there should be some singularity also inside this region. I mean, finite U. And this singularities means here we consider the low energy effective theory. So if the massless, extra massless particle appears, except this abelian gauge theory, then theory becomes singular. Theory becomes singular means effective field theory using U1 only, it becomes singular. So this singularity means that there is a massless particle. Actually, this infinity means massless particle at for the quarks and gluon. If A equal infinity limit, the gauge coupling is 0, so quarks and gluon becomes massless. Okay, so this represents quarks and gluon, massless quarks and gluon. But inside, somewhere in the moduli space, if we take some moduli at some value, VB of the U to some value, then there should be some extra massless particle. And actually, this should be with some argument. This should be a BPS state. So inside there should be some BPS state. Sorry, yeah, massless BPS state. Massless BPS state. For the break. Okay, sorry, yeah. Okay, so okay, take a break here. Yes.
Can you say again?
Uh-huh.
What was the idea? What did this mean? What kind of similarities are you discussing here?
Actually,
I made the argument.
actually, sorry. We will see. Yeah, this means there should be some singularities, and we want to determine what is the singularity inside. Later, next we will see what's. Yeah, this means because of the this infinity structure, coupling structure, there should be some singular points in the modular space. That is what.
What becomes singular when you talk about singularity?
Okay, yeah, it's what becomes singular means what becomes massless. Okay, actually the thing says some monopole, BPS monopole becomes massless at some point. I mean Z equal actually I will explain later, but plus ANE, and if this is 1 0, so Z equal AD for the BPS particle. This is mass. So if AD equals 0, then the monopole becomes massless. So the singular point is A or AD or some combination becomes mass 0. So that is a singularity. I will explain that, but yes. Uh-huh. Hmm? Uh-huh. Uh-huh. Uh-huh.
And W alpha also here.
Okay.
So this W alpha is
Uh-huh.
N equals 1 superfield.
Superfield. Yeah. Yes. Yeah. Yeah. Actually, yeah. Yeah.
To introduce two superfields, right? Because
Yeah.
you are in N equals 2, right?
Right. Yeah. So A include this W alpha and also phi. A is N equal to superfield. n equal to vector superfield. Yeah, n equal to vector superfield include n equal 1 vector plus chiral, 1 chiral. Yeah, yeah. This combination is this A. Yeah, yeah. And this, yeah, this decision is a bit complicated. I don't want to. This one, yeah. Yeah. But because in a low energy U1 field, actually there's a SU2, but here in a low energy equation FA, it's only include the U1 part. Yeah, yeah. But it's of course a composite, so it's in a strong coupling. It's not a weak coupling SU2 to U1 Higgs or something like that. It's something composite U1 things. Yeah. Okay. Sorry?
How do you compute?
I will say, yeah, something. I will explain a bit, but it's, yeah, yes.
And then you mentioned that when you have, in this case, A equals to the Z,
So for the BPS,
BA or BL, we preserve the supersymmetry.
preserve supersymmetry. Yes. So BPS state preserve some supersymmetry. Sorry?
In which sense you mean that they preserve supersymmetry?
Preserve. Preserve.
Commutator is zero, right?
Okay. Yeah. Preserve.
Or I'm wrong.
Yeah. Commutator. Yeah. Actually, yeah. For the vacuum state, all Q is 0. If this is not 0, it's called Suji breaking.
Okay, so you
Okay.
do that.
Yeah. This is a B is yeah. Okay. So this is yeah. It's called which keeps some supersymmetry. Yeah, it's like a vacuum. I mean, vacuum in a strange. Yeah, with charge. Yeah.
Why say has to be zero?
Has to be 0.
Yeah, because you explained that
Actually,
I
yeah.
have this case, so I have a BPS state
The massless BPS. Yeah, of course. Yeah, no. Some combination of NE. So
can be zero.
it can be 0. Yes. Actually, I will explain 0 too. One is monopole, 1, 0, and another is 1, 1, 1, 1 dione. It becomes massless. That is the conclusion of Sarva-Witten. There are two singularity, and it's a bit difficult to say why it's 2, but I will explain a bit, but maybe it's not so convincing. But anyway, yeah, it's from the string theory. There is some many arguments to show that, but yeah. Anyway, that's yeah. Okay.
I don't have a question. It's just
You don't have a question. Okay. Oh, sorry.
really for curious.
Okay.
Okay.
Okay. Sorry. 10分か。どうしようか。お。Good.もうそろそろ始めていいのかなよくわかんないんだけど、なんかいないからさ。いるローカリゼーションやったらね、まあ、 単に計算するだけだから、まあそれを見たら一瞬で、ああ、そうですか。いやー、っていうか一個も追えないからね、やっぱ S3 ですら計算何にも追えない。単にもう結果をただ言うだけで、うん、ほとんど何もやれないっていうか。基本は、いや、S3。テストのはもう全然何も言えない。うん、っていうか、その結果すら多分、結果を説明することすらできない。今村さんはペストンとか、ペストンのやつをレクチャーでやってるのは見たことない。うん。S3 とかだけだね。うん、うん。S3 とかだけ。うん。まあ今村さんのはね、ABGM とか、うん、そっちでやってたね。うん、まあ、そうかな。うん。まあわかんない。何の話？あは。あは。あは。あは。あは。そうだね。いや、っていうかね、単にね、もうディテールがいっぱいあるんだよね。むちゃくちゃ。で、何が重要なのかあんまりよくわかんない。もうこれは、この話は絶対しとかなきゃいけないと思うから、まあその方が、エグザクトリザルトで、うん。っていうかそもそもね、ローカリゼーションっていうか、エグザクトリザルトっていう、なんか、ローカリゼーションっていうタイトルで、とりあえず書いときましたとか言って何も聞かれずに書いてて、ちょっと、広いね。広いね。ローカリゼーションっていうのはね、ほんとテクニックでね、物理が何もないんだよね。それ自体には。だからやっても、まあそうなんだけどね。本当に使う人はあれなんだけど、使う人は別にレクチャーで聞いてもあんま意味なくて、単に自分でやんないと意味ないから。はは単にインデックスね。いや、そうだったら別に結果見るだけでいいから、特に何もしなくて、こうなりました、終了で、特に何も言うことがなくなってしまうので、いや、どうやってやるかっていうのをちょっと言わないといけないんだけど、まあ、とりあえずけど、数字の話はある程度、なんか慣れてないとそもそもね、わかんないんじゃないかなと思って。は、は、は、は。だから、ある程度最低限はしといた方がいいかなっていうふうにちょっと思って。OK. So let's start, Okay, let's start. Yeah. Okay. Hmm. Okay, so actually there is a symmetry in this theory. It is a U1. There is a U1R, but it's anomalous, and it's broken to the Z8, and it acts U2 due to minus U. So there should be at least two singularity. Actually, U equals 0 is not allowed because some consideration for the positive gauge coupling constant or something like that. And then the minimum possibility is 2 singularity. And as a convention, we say at U equal lambda square. Actually, this lambda is not one loop something, but maybe something. But here, just take this is lambda squared. Actually, there's only the scale, mass scale is this lambda, so there is some proportionality 2 pi or something like that, but I forget about it. This denote like U equal lambda squared. And then, monopole massless because actually we can rotate SL to Z, so we can. So this is a convention, and then theory around the singularity becomes super QED because U1 gets plus this BPS massless particle. So it's described by n equal 2 vector ADWD alpha D and n equal to hyper M tilde with the superpotential. Okay, this forms the superpotential needed to keep n equal 2. For the vector n equal to vector multiplet case, there is no superpotential, but for the hypermultiplet, we need some superpotential. And this coefficient also fixed by the n equal 2. Okay, and then, then we can see around here the monodromy matrix is like this, and then M infinity should be M1 times M minus 1 because if we rotate around the whole one, then it should be 1. So this is the relation. Then M minus so M1 is at U equal lambda squared. M minus 1 is U equal minus lambda squared minus 2, 3. Then this is a dione. Charge is 1 comma minus 1. Becomes massless. Okay. In a classically, there is in the modular space there is a one singular point at origin, but actually because of the quantum mechanical non-perturbative effect, it split to 2. And theory is almost always becomes U1, not non-abelian, like n equal 1 supercommon theory case. This theory is everywhere U1, but at this point there is some massless particle coupled to the U1. This is yeah, of course here we assume there are only 2, not 4, 5, 6, but we can say, we can argue these are only the solution with some physical consequence. Then now singularity are determined. Infinity and the finite position. So it's like a hypergeometric function. If we found what is the singular behavior at the point, then we can find what is a holomorphic function, analytic conjugation of that function. Okay, so now if we have a all singularity structure, so we should, in principle, determine using holomorphy, of course. Okay, so now, yeah, we have F pluripotential in principle. But there's some interesting things for this solution. Actually, we here consider the torus, or it's represented by the this one. Actually, torus or the Riemann torus, or this is a Riemann surface, because we just consider the complex structure. Okay. Okay. So more precisely, this is not torus, it's a Riemann surface with genus 1. And this is called Seiberg-Witten curve. Seiberg-Witten curve, and if we define it's called Seiberg-Witten one form. Okay, so nice property of this one is du d lambda is holomorphic. It's regular. Actually, there is only regular function, and then we can see this gives A and AD by this. Of course, this alpha and beta is one cycle. This is alpha cycle, and this is beta cycle of the torus. Okay, and then tau equal so because of this properties, this tau in effective coupling constant, non-perturbative determined, should be this one. And this is, by this definition, become this one. So this is one form, regular one form over this cycle. And it is known that this combination, this combination is tau of this torus. Tau is a modular parameter of the torus. Okay, and of course, then this torus and Riemann surface, there is a SQFT acting, and this SQFT is the same as the SQFT we are discussing for the U1 duality. Okay. I will not explain, but actually, this is there is a singularity at x equal lambda squared, x equal minus lambda squared. Because this x equal u, there is a double 0 in this torus. Then it's a singularity. It means there is some pinching occurs. Then this cycle becomes a pinching. Then it becomes equal 0 because there's a pinching. Okay. So this is a very convenient expression for this f in a torus. But in original Seiberg-Witten works, this is just a coincidence. We don't know why this torus appeared in n equal 2 supersymmetric gauge theory. But later, this is related to 2A gauge theory on Calabi-Yau 3, and take rigid limit. Rigid limit in the Gn goes to 0 limit, then gravity decoupled. Then this we have on this Calabi-Yau 3, we have n equal 2 supersymmetric gauge theory, and this torus. This torus is some deduction of this Calabi-Yau 3. It's by the Cauchy buffer originally, and some, and also if we consider M5 on some Riemann surface and take the Lorentz limit, or we can replace this M5 by the 62,0 as a Pacomari field theory. Then we also have, in this case, we also have some n equal 2 supersymmetric gauge theories. And then this sigma is this torus, or Riemann surface here, in general. So from the string theory, this algebraic geometric structure is very natural and explained. Okay, and this is some non-perturbative analysis in n equal 2 case. Okay, and if we add this theory to the n equal 1 mass perturbation, then we can explain the confinement in n equal 1 theory by the dual Meissner effect, because of this massless monopole can condensate at the singular point and 2 point. But I will skip that one and go to the part 2, the index and the localization. Okay. Okay, no problem, no question for that. Actually, the index or the localization, yeah, this is just a technique to compute some correlator or partition function in the theory. And here we cannot use a superfield. We should do the component field. So the every calculations are heavy or messy. They're actually super messy. So, but yeah, I explain some simple model and most simple case that is n equal to 3D theory on S3. But then, okay, I will explain something about that. But first, I will explain about the index. Actually, index and localization techniques are almost same notion. Okay, Witten index. Okay. Sorry. And there is some, of course, a reference. Oh my gosh. Reference. Okay. Oh. Okay, there are many differences anyway, but actually there are many fields. I mean, yeah, localization can apply almost all supersymmetric theories. So there are many results, and so. So this is some reviews by some several authors, 10 or 12, I don't know, under 700 pages. But it includes many things. So if you are interested in some specific topics like AGT, factorization, everything, so then you can consult this one. Okay. So now I will explain what is a Witten index. So assuming this algebra in operator formalism of the quantum mechanics or field theory, okay. Of course, this is realized by the supersymmetry. And sorry, and okay. Assuming these algebra, of course, these are represented by the supersymmetric algebra. This minus, yeah, this means Q is fermionic. Actually, this is just a projection operator. Okay. This divides fermionic states and bosonic state. If we say this +1 eigenvalue states are bosonic and -1 is fermionic. Okay. Then consider these things. Then Okay, this is H here. It's a Hamiltonian we call Hamiltonian, and this is this one, +1 or -1 for fermionic bosonic state, and trace is over the O state in the theory. This is a trace for the all state. This is in a operator formalism, and T is just a parameter. Okay, this is just a constant parameter. Then this is T independent. Any T equals 0, T equals +1, infinity, everything are same. Now this is a Witte index. Okay, and then I will show why this happened. If we define the QB, QB is not a good name, but anyway, this combination, this is, then argument is a bit simple. Then this operator is Hermite, of course, by definition, and QB squared equal H. Okay, and of course this is non-negative because the QB is Hermite, and H, this is written by the square of the Hermite operator. This should be positive. Okay, and then let's consider subspace. So let's consider some subspace with a fixed energy. Yes. Sorry, theta? Theta where maybe I this one Q? Q? Q. You mean alpha or something like that? Actually, yeah, Q can be anything. For example, Q can be Q1 or Q2, anything. If we, here if we assume just this algebra. This one? Why this combination? It's to argue this is independent. Okay, but at least we can consider such combination. Yeah, it's of course it's something not good representation of the rotation symmetry or something like that. But it's okay. Actually, just I assuming this one, and consider such a combination always. Of course, if you want, you can introduce some good combination to QQ. The guy is some good one or something. But anything, any operator satisfying these algebra is okay. I think, yes. And then, we call B and F as some state which satisfy this relation. I mean, this is bosonic and fermionic. This is just a projection operator, so eigenvalue should be +1 or -1. Okay, this one. Then, for any this bosonic state in this Hilbert space, but if E is non-zero, then you can associate this QB B. So this should be a fermionic state because QB is fermionic. I mean, because of this relation. This is a negative eigenvalue for this operator. Okay, this should be 1 to 1 because we can map this state to the B again, asking QB. And also, same things for F. Okay, then every bosonic state have a fermionic state. Okay, so bosonic and fermionic state always paired and have a same energy or Hamiltonian. Then in this here is a bosonic and fermionic. This has a same H but different signs. So it cancelled in this trace. Okay. So these states do not contribute to Witte index. Then this index is T independent because for zero mode this vanishes, so there's no T dependence. Okay, so it shows this Witte index is indeed T independent. And for the zero mode, this is of course this is a Hamiltonian. So that means okay. So there is no error for the zero mode. This is if we act QB to the zero mode, then it's vanished identically because of the algebra. Okay, then or we can reverse this argument. So the zero mode is a QB closed state. This means this. And there's a, maybe this is not needed for you, but QB, okay. Yeah, you can say that. Here I want to say that the QB exact state. Anyway, so this with the index. So this index counts number of zero mode. Okay. So this counts just the number of the zero mode with a sign for the boson and fermion. So the meaning of the index, or SUSY index, or with the index. And this is quantized, so we expect it is invariant under the small deformation. There's no continuous dependence. Actually, there's a pair structure. So if some massless states become, massive state become massless, or zero, it becomes zero mode by some continuous continuous deformation. But that zero mode should be paired because it's paired at the massive state. So then, such a paired zero mode doesn't contribute this one because of this fact. Okay, so small deformation or doesn't change this index. So this index is very rigid in the theory. Okay, so that means this index can be computed at any coupling constant or some inner parameter of the space. We can compute it in a weak coupling limit or something like that. Okay. So this is why this quantity can be computed non-perturbatively. We can compute it any parameters. Anywhere in the parameter space of the theory. Okay. So then here generalize this with the index a bit. Let us consider this one. This is a bit changed from here, like here. Here, we assume further there is no Hamiltonian, but if we take this V as a QB, then it becomes QB square, so it's same as this one. But here we assume these properties. OA is Q exact, Q closed, and V is commute with QB squared. And then we can say this is T independent also. Okay, for any O or V. So these types of the index appeared as elliptic genus, superconformal index of the 4D n equal 1 or something like that. Yeah, anyway, its structure is like this. Sometimes it's called, this OA is called the chemical potential in the superconformal index case. or q2 something. Yeah. Oh, sorry. Times okay, this is just take a derivative with t. Also QBV is commutative with itself, so here we write down like that. Then is okay because QB commutative with OA and QB also okay, there is something here. We use this is Jacobi. This one? Here? Here? Oh, sorry. Oh, I'm sorry. Okay. QB, commutative of the QB and this whole things. Okay. Here we use a Jacobi identity. Actually, computing this one, QB, this is anti-commutator, commutator. Okay. So then we can show by explicit computation of Jacobi identity, it's QB squared, commutator of the QB squared and V. Okay. And if here we assume QB squared and V commute, so it's 0. So this is 0. So QB commutative with QB V here. Sorry, this. Yeah, okay. Okay, so then this anti-commutator becomes here because we can move QB left or right. So then, of course, this is 0 because for any operator here, A, we can show this one is written by, of course, expanding this one like this one, QBA plus QB minus 1A. And this is a trace, so we can take a QB, this QB to this side, and then QB and A. Sorry. Oh, it's not true. Yeah. QBA. Okay, here, yeah, we already changed this QB. Then this is anticommutative minus 1 FQB here, okay, times A. And the QB and minus F are anticommutative, so this becomes 0. Okay, so this A is this whole things, so this is 0. Okay. Sorry, could you speak again? Bosonic. V. V is actually anything here. Actually, yeah. We here, yeah. The bosonic or fermionic means minus 1, what's equal 0 or equal 0. But here we have not used anything for this assumption. So, you mean t goes to infinity limit? Here. Yeah, this A. Yeah, I think this uses just a trace. Trace can be O1, O2 equal trace O2, O1. There's no minus 1F appears here, so it can be anything. Yeah, in general. But of course, yeah, in a practically, this V should be a fermionic operator. But yeah, like QB. But in this computation, we can apply this to the any systems. Actually, such a types of argument, yeah, actually not, if there's no supersymmetry case, we can apply, for example, the low energy flexibility SYK, Witten Stanford applied such, I mean, the localization technique similar to this one, to the such theories or anything like that. So, yeah, this is some, yeah. Here we use just algebra, so I think it's okay. But maybe there's some wrong point, but yeah, practically this V should be fermionic. But this one? Okay, sorry. This is final one can be divided by trace over minus 1 FQB times A, and this is 0. Okay. 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 So this. So this is a generalization of the Witten index, including some chemical potential or operator here, and take any value here. Okay, this is actually here. This argument is is analog of the localization computation. I will render it to this case. Anyway, okay. So in this case also, we can take t goes to infinity limit or something like that, and this is also quantized and paired or something like that. So it doesn't depend on the deformation of the theory. We can change compactification, radius, superpotential, coupling constant, anything. And we can compute it anywhere. Here, this index is defined by this operator formalism. Operator and state, or something like that. That means, of course, yeah, this is related to SUSY QFT on S1 cross MD minus 1. That means there is a S1. Because we need to I mean, using operator formalism, we have a time direction. Okay. So this depends on the time direction, actually Euclidean time direction. Okay. So the theory on this type, we can apply this index. But theory on, for example, S3, S4, or something like that, or any other, we cannot apply this one directly. Okay. So in path integral, we can consider any manifold. And another thing is in, for example, S4 or S3, then this analogs of this index can depend on the parameter. So it's not like a topological. Okay. This is a, Peston first showed for the S4 case. N equal 2 gauge theory on S4 case. And actually that example is very, very complicated. So I will not explain about that. But yes. This one. Yeah, because this is time. Times, okay? We should quantize theory. So yeah, state is state on this space, okay? Okay, so then we go to this one to the path integral formalism. That is called the localization technique. Okay. Actually, here we can introduce a localization technique from the mathematical theorem called Duis-Summon. But for the usual integration of the space, but here we go through this index anyway. Okay, the assumption is something similar to this one. First, okay, maybe I'll stop here. 1:30, okay. Okay, so thank you very much.